Okay, I'm here to talk to you about the electrostatic force. And we've seen some of this already, like charges attract and opposite charges repel each other. And we talked a little bit about neutral objects, which in theory don't attract or repel unless you take electromagnetic induction, unless that affects one of the objects, in which case you can get an attraction. But we're not going to deal with that really. We're just going to look at the basic attraction and repulsion of objects. And there's a form for this, an equation, that's F sub E, which is the electrostatic force, equals K, Q1, Q2 over R squared. And before I talk about the variables in here, I want you to compare this to the gravitational force equation. F sub G equals G M1 M2 over R squared. You'll notice that they're very similar. G is a constant, was the first value on your reference table. Well, K is a constant too. K is what's known as the electrostatic constant. And if you look on page 1 of the reference table, you will see this number, 8.99 times 10 to the 9th newtons meters squared per Coulomb squared. So the electrostatic constant, you can find that on your reference table right there. This one had a mass 1 and mass 2. So you're looking at the two objects have masses, those masses attract each other. Well, here, if you had two objects, like, a positively charged one and a negatively charged one, they actually would have, assuming they had mass, would have a gravitational force of attraction. It turns out that the gravitational force is much, much weaker, generally speaking, than the electrostatic force. So if you look at two protons, or a proton and electron, the gravitational force, and you can find the mass of these objects on the reference table, the gravitational force between an electron and a proton is much, much smaller than the electrostatic force. And part of that is this constant here, 8.99, is just much, much bigger than this constant here, which is 6.67 times 10 to the negative 11th. Negative 11th as opposed to positive 9 gives you almost a power of 19 difference. So they have a force that, in this case, if they were opposites, would cause one to be attracted to the other. They would both have a force towards each other. And it would depend not on their mass, but on their charge. And their charge we're measuring in coulombs, not in elementary units, so you want to make sure that you convert them to coulombs if necessary. And both objects are affected. If you look at the third law, for example, it says that the forces are equal and opposite. So even if one had a big charge and the other one had a little charge, they would still have the same amount of force acting on them. Their acceleration might not be the same, depending on their mass, but the amount of force should be exactly the same, regardless of what these pluses and minuses are. And the last thing that we see is R, which is equivalent to distance, just like in this particular gravitational force equation. And both equations follow what's called the inverse squared relationship, where the force, if you graph force versus distance, for example, F versus R, you get an inverse squared relationship. Looks exactly the same for both of them. Meaning, as you go further away, the force decreases exponentially. So doubling the distance, for example, gives you a 4 times weaker force. And halving the distance, meaning you're twice as close, basically, gets 4 times stronger force, etc., etc. You triple the distance, 3 squared is 9, so tripling the distance is 3 times stronger. A third of the distance would be 9, tripling the distance would be 9 times weaker. Taking the distance to a third of what it was would be 9 times a stronger force. So either way, if you graph force versus charge, for example, you should get a linear relationship because force is directly proportional to the charge of one of those objects. Just like in that equation, if you graph force versus mass, you get equation 9. Now there is one important difference in these So let's take, for example, I'm about to erase this, so pause and write some stuff down if you need to. Is that gravitational force is always going to be attractive, as far as we know, and electrostatic force is not. So, for example, if we had positive charge and a positive charge, we looked at the forces on them. Well, they're both going to have a small gravitational force that's attractive towards each other, F sub g, but they're both going to have a much bigger repulsive force, and these are not to scale. So they're going to repel each other. The F sub g would actually be much smaller than this, probably. So they would repel each other, and the forces would be in opposite directions. If they were of the same charge plus opposite charge, plus and a minus, they're going to both have an F sub g towards each other, equal and opposite, and they're going to both have an electrostatic force towards each other, because opposites attract. And we'll see more of force problems in class. I think that does it for this video, so thank you very much for watching.